All right, so as I was saying, the first hour would be recap, possibly even less than 1 hour. So we have a bit more time for the 2 degrees of freedom system, which are embodied in the vibration absorbers, really, because that's what they are applied for. And so let's start with a recap very briefly. So we have this equation here, which you might recognize as a second order differential equation. Very easy. And if you can always turn it in this way, you can always write something that looks like this for every second order differential equation. And every second order differential equation will be solved, well, a constant coefficient that looks like this will be solved with this, in this form here, this solution here. And as you can see, this has a sinusoid, the blue part, that is decaying exponentially. So this is an exponentially decaying sinusoid, but this applies, of course, if you have an so-called underdamped solution. That means if zeta, this zeta here that you can find here, is smaller than 1. What happens if zeta is equal to 0? If zeta is equal to 0, this term goes away, and you are left with the ordinary undamped free vibration equation. And if you turn zeta is equal to 0 here, this e to the power of minus something goes away, e to the power of 0 goes away. And omega d, which you remember was just omega d, was just omega n times the square root of 1 minus zeta squared. This omega d becomes omega n effectively. And so you back up a simple sinusoid with omega n, with amplitude a, and frequency omega n, which is the natural frequency of the system. So as you can see, if you have damping, a system doesn't vibrate freely at the natural frequency of the system. It vibrates at a different frequency, which is very close, because 1 minus zeta squared is almost 1, but it's not exactly 1. So when you that means that when you measure anything, when you count how many, when you count the period, that means that you are observing omega d. You will never be able to observe omega n. Okay, so just so you know that if you take any measurements, you will always be measuring omega d, because that's the frequency of oscillation. Which again, if it's slightly damped, it might be extremely close to omega n, but it will never be the same as omega n. All right, we will not be caring about critically damped and overdamped, although you should know about it. You should always know about it. We will not be doing it in this tutorial, but it doesn't matter. It's just a solution in a different form. As long as you know which solution to use where, it will be fine. Let's start with solving the this tutorial question here, this one. We want 4 and 6. So we want question 4 from TTS 10, which is, again, it's one of the tutorial questions you've done in second year, I'm sure, because it's the same tutorial sheet. We have a disk with a polar moment of inertia of 6 kilogram meter squared, and is supported at the free end of a wire 1 meter long and 10 millimeter diameter. We also know that G, the modulus of rigidity for the wire material, is 80 gigapascals. The disk is damped by means of a dashpot, and the ratio of successive amplitude is 1.5 to 1. We want to find the shaft stiffness, damping coefficient of the dashpot, and the transient frequency. Now, the transient frequency, you should remember, this is just a different notation to refer to the damped natural frequency. So in omega d, that's what it is. It's called transient frequency because it's the frequency of the transient while this thing is freely decaying, because at some point it will become 0 at steady state. So while it's transient, it is vibrating at omega d, so omega t, omega transient. All right, so let's start question 4 very briefly, very easy. So what we have is, let me go back here, a disk with a certain polar moment of inertia. Let me do this very briefly. So J of the disk is 6 kilograms meter squared. and the length is 1 meter. So say 1000 millimeters. Well, let's say 1 meter, because everything is in kilogram meter squared anyway. And phi, the diameter, is 10 millimeters. The modulus of rigidity is, so G, that's 80 gigapascals. The disk is dumped, and we know that the ratio of two successive amplitudes, so the amplitude of the oscillation n divided by the amplitude of the oscillation a n plus 1 is 1.5 to 1. So a over n, sorry, an over an plus 1 is 1.5 over 1, basically, so it's 1.5. And we want to find the shaft stiffness. So what is KT, the torsional stiffness of this shaft? I want to find the damping coefficient, which is C. Remember, C is the damping coefficient. Zeta is the damping ratio or damping factor. And the transient frequency, that's omega d. Okay, so this is the tutorial question. There you go. We need to find these things. Knowing all these quantities. Now, let's start with the torsional stiffness of this shaft. This shaft, of course, it has a certain diameter, there's a certain length, and you know that if I twist it, it will give out an angle of twist. So what is the equation for the angle of twist? So this comes from the stress analysis, and the angle of twist phi. Let's not call this phi. Let's call this d. So the angle of twist phi is TL over GJ. You should remember this. Now, what is the stiffness? Remember, force is Kx, so the stiffness is force over displacement. Now, this is linear stiffness. We want torsional stiffness. Now, torsional stiffness is the torsional equivalent of the force, which is the torque, and the torsional equivalent of the displacement, which is the angle of twist. So if I rearrange this to have T over phi, this becomes GJ over L. And this is also the torsional stiffness. This is also KT as a subscript. That's it. We have G, we have J, we have L. That's it. We don't need anything else. Okay, I will leave the numbers to you. Okay, so all you need is to know these things, and this is what we found. We found this number here. This is just a number. Let me spell it out. This is a certain number of Newton meters per radian, because the torsional stiffness is not in Newton per meters. Torsional stiffness is torque over angle, which is Newton meters per radian. All right, so I don't need this anymore. What is C? What is the C? Well, we can find C, remember, but by using the critical damping ratio, which is 2 omega n times m, which in our case is 2 omega n times what? That's times J. Oh, just a second. This J is not this J. This is the mass moment of inertia. Just to be clear, this J, I called it J, but this is in meters to the power of 4. So this comes from D. This J is pi d to the power of 4 divided by 32. This J, this that I called J, is in reality is IO. Okay, well, generally it's a polar moment of inertia, so we call it J as well. But in this case, we have a clash of notation, so let's call it IO. So in this case, this IO is the mass of this equation here. It's the mass that goes in front of the acceleration. So this is not the mass, is the rotational equivalent of the mass, which in our case is IO. Okay, just swap it. And what is omega n? Well, omega n, we know that this should be k over m, but that would be the translational omega n. We have a rotational omega n, that would be the rotational equivalent of the stiffness, which is the torsional stiffness, over the rotational equivalent of the mass, which is the polar moment of inertia. See, let me spell it out here. This is called polar moment of inertia. And this one would be polar moment of area. This has units of kilogram meter squared. This has units of meters to the power 4. Okay? Not the same thing. Definitely not the same thing. Okay, so we have C critical. Do you agree with me? We do have C critical. That's fine. That's nice. So what we need now? We need to find C. But remember, zeta is C over C critical. So that means that C is just 2 zeta omega n IO. Do you agree with me? Just rearranging the equation. Now, 2 is a number. Omega n we can find because we found KT and we have IO. IO is a number again. Zeta we don't know. But we can estimate zeta by looking at the ratio of the two successive amplitudes. Since we know that this is exponentially decaying, we know that there is a ratio between this amplitude here. There is a ratio between this amplitude here and this amplitude here. This is AN. And this is this successive. This is AN plus 1. Since we know this ratio, we can estimate what's going on in this curve. And we estimate it using the logarithmic decrement, delta, which is the logarithm. Come on. I can make it. There we go. The logarithm of the ratio of two successive amplitude. And that's equal to, well, approximately equal to 2 pi zeta. So the left-hand side is completely known. We can find zeta. And so we can say that C is, well, let's find zeta first. Zeta is a number which has no units. So zeta is delta over 2 pi, which is equal something something. And this is important because now that we have zeta, we can find C. So C is equal to 2 zeta omega n IO, which is also something something Newton meter second over radian. That's for the torsional damping coefficient. And finally, the last bit that we have to find is omega d. But omega d, as you know very well, omega d is just omega n times the square root of 1 minus zeta squared. So this is also something in radians per second. Okay, I will leave the numbers up to you, but as you can see, it's very easy to find all these things. It's just a matter of using your formula sheet, basically. That's what it is. And understanding what's going on. All on board with question 4? Very good. Let me check the chat. Nothing in the chat. All right. So let's do question 6. Not this one. Question 6. A machine of mass 500 kilograms is mounted on a rubber mat which deflects. Let me copy all these data in. This is question 6. So we have a machine of mass m 500 kilograms. is mounted on a rubber mat which deflects. So let's call this X0, 2.725 millimeters due to the pure weight of the machine. But when we displace it and release it the vertical amplitude decreases by a factor of 10 every 2 complete oscillations. That means that the ratio of not the successive amplitude, but the amplitude after that is 10 to 1. So AN divided by AN plus 2 is 10. You agree? So I'm right here that AN over AN plus 2, this ratio is 10 to 1, just 10. Assuming that we have viscous damping, determine the damping factor, that's zeta. Determine the damping coefficient, that is C, and determine the transient oscillating frequency, that is omega d. There you go. Looks like we are missing one thing. We don't know K or we don't know omega n. If we knew either K or omega n, we would be able to solve this quite easily because zeta comes from the ratio of the amplitudes. That's fine. The mass is given, but we don't know the stiffness. Or do we? We do know the stiffness. It's hidden. It's hidden in the fact that we have the deflection. So let's do the free body diagram of this machine. And you know that this thing deflects 2.725 millimeters under its own weight. That means that the spring is compressed by 2.725 millimeters to balance the gravitational force. Do you agree? So if I do this, and this is M, and this is F, so this is the gravitational force, mg, this is kx0, and these things, I'm saying that these two forces are balanced. And so that means that K equals, well, if we do, the equation is mg, sorry, kx0 minus mg equals 0. So I can find K equal to mg divided by x0. And this is a certain number of newtons per meter that I will leave up to you to find out. And now that we have this, we can easily find omega n, because omega n is the square root of k over m. And then we use the logarithmic decrement, which we use in its general form now, which is 1/2 log of an over an plus 2 equals almost 2 pi zeta. And so we can find zeta being equal to delta over 2 pi, more or less, approximately equal to delta over 2 pi. And this is also a number with no units. And then we find C. Remember, C is always, we can always rearrange zeta, the definition of zeta, to be C is 2 zeta omega n m. So this is also a certain number of Newton second per meter. And omega d, well, omega d is very easy. It's always the same formula sheet. Go there, omega n square root of 1 minus zeta squared. There you go. And this is a certain number of radians per second. Questions? I believe the hardest part of this question was figuring out that the stiffness information was there all along. Yes.
If it was like an plus 3, would we divide the logarithm by 3?
Yes, because remember the equation is 1 over R n plus R. Okay, this is the equation. What does viscous damping mean? It means that we are using this definition of zeta. So zeta as where is it? So the zeta, because if you have, I'll show you next week, but viscous damping means you have a dashpot, whereas some materials have hysteretic damping, which is structural damping. The good thing about dashpots is that the damping increases as you go up in frequency linearly, whereas the structural damping has the same level of damping no matter the frequency level. It would be clearer next week. Don't worry. We will do damping models next week, and it would be much clearer what's the difference. Okay, that's it. Done. Easy. Now let's go to not these ones. Let's go to DTS11. That's because DTS11 contains forced vibrations. So far, we have only dealt with single degree of freedom vibrations that were freely decaying. And now we will do 1, 2, 3. We'll do the first 3 of these, but first I'll give you a small recap of forced vibrations. So for forced vibrations, the equation becomes this one. Always the same, of course. But we have one added problem. I would say problem. Now, the important things here are F0 and omega. Omega has got nothing to do with omega n. Just these two things are completely separate concepts. Omega n is a property of the system. Omega is a property of the external agent. So it doesn't have to be the same. It can be any omega. In fact, if that omega is 0, what happens is that that force is applied statically, just a static force applied to it. Whereas if that omega, we'll see now that if that omega is omega n, then we are in trouble. In fact, the solution to this, and I will just look at the steady state solution, which I will call xp, which is the particular integral of this thing, is given by capital X sine omega t minus theta. Whereas capital X is the amplitude of the final oscillation, and theta is the phase of the response with respect to the force. So if the displacement is going in the same direction as the force, following the force, they will be in phase, theta 0. If I am pushing against the swing that's coming back, that would be theta 180 degrees. So the force and the displacement will be out of phase. And at resonance, the force will be in quadrature. That means 90 degrees away. So it's exactly in between out of phase and in phase. And that is where you are pumping energy into the system continuously without even realizing it. And so the system, the energy in the system keeps increasing and increasing and increasing, and then something breaks. Okay, so let's see what are the shape of this x and this theta. Now this capital X looks like this, F0 over K. Now this F0 is not the same as this F0. This one is capital F0. Capital F0, sorry, this small F0 here is capital F0 divided by m. Because we have divided everything by m in order to get rid of this first coefficient here. So if you divide everything by m, you can rewrite everything in terms of these. So the same F0 that you get in the equation is not the same that you'll get from the force. This capital F0 is the actual force in Newton, the amplitude of the force in Newton that you are applying externally. This one is a force normalized by the mass. Okay, so this is Newton over kilograms, this F0 here. So this is F0 over K over a big ass square root. And that is 1 minus rho squared plus 2 zeta rho squared, where rho is the ratio of the external agent omega over the natural system omega. Okay, so omega n. And zeta is zeta. Okay, can we have a plot of this? Arnaldo, can you please plot this for me in terms of rho? Yes, I'll do that right now. If I plot this in terms of, so this is x, and this is rho. So we have rho equal to 1 at some point. Okay, rho equal to 1 means omega equal to omega n. See what I mean? So when the external agent is forcing the system at the natural frequency, we say we are at resonance. It's a bit more complicated than this, and I'll show you why now. So this will look like this. Something like this. And this is at damping level of 0, when zeta is 0. Look, if zeta equals 0, this part of the square root goes away. And this is just 1 minus rho squared. Because, sorry, this, I missed the squared here. That's right, it's 1 minus rho squared squared. So this denominator becomes 1 minus rho squared only. And see, when rho equals 1, the denominator approaches 0. And if it approaches 0, that becomes that means that if you're approaching from this side, you get to plus infinity on the left and plus infinity on the right. Okay, so it explodes effectively. If you have more damping, if you have a zeta that is non-zero, what happens? Well, if you have non-damping, more damping, some damping, this is up. Oh, redo. There you go. So this happens when you have more damping. Now, what do you notice here? Apart from the fact that I'm bad at drawing. What do you notice? You notice that the peaks are not at 1. Depending for a certain, at each level of damping, the largest amplitude is not when rho is 1. The largest amplitude is when rho is 1 only if zeta is 0. Okay? So these peaks, this one, and this one, as you can see, they shift left. As you keep increasing damping, so if you increase damping, if you increase zeta, these peaks shift slightly to the left. Now, this is very exaggerated. They don't shift a lot, but they shift in a way that you can't ignore. So this is what defines the resonant frequencies. So this is omega r is omega n times the square root of 1 minus 2 zeta squared. You see? So omega n, omega d, and omega r are three different things, but they're all close to each other. So sometimes you see the engineers might confuse them. That's because these engineers are confused. Okay, they are three different things that mean they have three separate concepts. Omega r is specific for forced vibrations. It doesn't exist if you just let it freely vibrate. So the resonance is something that has to do with external factors, external agents. Okay. Sometimes we say, oh, that's the resonance frequency of this system, but this should be the natural frequency of the system. That's the property of the system. As far as you have mass and stiffness, you have a natural frequency. If you have damping, you also have a transient frequency of oscillation that you can observe by oscillating. The largest amplitude you get out of a forced vibration, that is happening at resonance frequency. Okay, and you can find it easily if you find the maximum of this function with respect to rho, with respect to omega, you find exactly this. Basically, you can try it yourselves. Let me check the chat. Show at the end where the system is settling, green line be above all. Then what do you mean settling? No, it's not settling. It's just settling earlier. But if you have more damping, then the resonance occurs earlier. And again, this is exaggerated. They are very, very close to one anyway. All of these are very close to one, but these form a parabola. So if you join all of these points from here to here, they will form a parabola. If you want to break a wine glass, you play a sound such of, yeah, exactly. So if you want to break a wine glass with a speaker, what you do is estimate your damping ratio of the glass. Then you find the resonance frequency of the glass given the damping ratio. And then you can just play a tone, a pure tone, which is a sine wave. That's a pure tone at that frequency. And it might not break, but it will give you the largest possible amplitude at that mode shape. Okay. Now, if that's enough to break it, it depends on the damping. See, because if you have a lot of damping, it will never break, because this amplitude might not be enough to break it. In fact, if you're holding it, it will never break. Just the simple fact of holding one object increases its damping level by a lot, because your hand gives a lot of damping to the structure. And you can feel, because if you put a glass on the table and you tap it, it goes like ding. If you hold it and you do it, it doesn't do that. Does it? Okay, you try that. That ringing sound, it's ringing because it keeps going, so it doesn't die out very soon. So you can hear that ding. Yeah, try that, and it will be much clearer when we do the experiment in week 8, when I hit the structure with a hammer, and you can hear it. You can hear it ringing. All right. Yes, that's how we make things vibrate. We hit them with a hammer. I'll show you. That's a very fun experiment. All right, but increasing damping causes more oscillations. What do you mean causes more oscillations to the system on the isolation phase? I'm not sure what you mean by causes more oscillations. I think it causes less oscillations, but fewer oscillations. If you want to explain, I'll read it. But I want to draw another plot first. And the other plot is theta, because we are neglecting the fact that we have two things going on, x and theta. So what is the plot of theta instead? The plot of theta as a function of rho always, it looks like this. And let's say I'm plotting minus theta. Okay, so it looks a bit better. So you start from 0. This is your 0 level. and then you get here, and then it jumps straight down to -180, and then it goes on. So if you have no damping, whatsoever, this is what's happening. If you are on this side, your force is in phase with the displacement. If you are on this side, your force is out of phase with the displacement. 100% in phase, 100% out of phase. There is no in between. Because if you are in between, everything explodes anyway. If you increase damping, what happens is this. So this starts very close and then suddenly drops down. Something like this. So it gets eased a bit. And it gets eased more and more the more you increase damping. So it will start dropping off earlier. But what can you observe? This is very odd. This is very wrong. Not like this. Okay. So what do you observe here? They all pass through one point. What is that point? That point is exactly -90 degrees. Okay. Hamza wants to ask a question. Of course you can ask the question, Hamza. Please go ahead. And while you ask the question, I'll show you what does it look like for theta. For theta is just the arctangent of, look at this. This is Pythagoras theorem in disguise. So this is just opposite divided adjacent. There we go. Nice. Does the wheel diameter affect the torque? Oh, right. So it's not related to this tutorial. So you'll ask me this later. Okay. The wheel diameter, no. Anyway, the wheel diameter doesn't affect the torque. Not the external diameter of the wheel, at least. It's the internal diameter that does. Yes, the hub does. Are you doing the coursework while I have the tutorial? You are incredible. You are incredible. I don't know you, Hamza. Okay? Okay? You don't know me. I don't know you. Okay? All right. Okay, we can solve it. We can start solving the question. So let's go to tutorial. I don't care about this anymore. So this one. We have a system that may be modeled as shown in figure 1. We have extracts from the response data when it's subject to a sinusoidal force of constant magnitude as follows. So when we are forcing this with 800 newtons with a certain FF, says there. So at 67.7 hertz, the X we get is 7.07 millimeters, and the theta we get is 45 degrees. If we go at 100 hertz, we get 10 millimeters out of it, and we get 90 degrees. And if we go at 147.7 with our force, then we get 7.07 again out of it, and 135 degrees. You want to find the natural frequency, damping factor, support stiffness, mass, and damping coefficient of all these things, just looking at the data. So how do we find this? Well, if you look at what I've drawn here, it says that we have 90 degrees, see, 90 degrees, 10 millimeters at 100 hertz. So I suggest that we are here. I suggest that we are here. Okay, we are not at the maximum, we are not at the peak, but we are very close. And that's because I know that the only possible way for this to get to minus 90 degrees is at rho equals 1. That's the only way it's possible. Rho must be equal to 1. And so I know that the middle row is that. And also, I also know that rho is 1. That means that omega is omega n. You agree? And so omega n, the natural frequency is 100 hertz. And it is. It is because it's where theta is 90 degrees. Nice. How do we estimate the damping factor? Something that you might not have seen is that what is the damping factor in this thing? See, if I increase the damping factor, the sharpness of this peak decreases. The smaller is zeta, the sharper is the peak. And so by looking at a point to the left and a point, well, a particular point to the left, when we have, say, 45 degrees, and a particular point to the right, when we are at plus 45 degrees, well, 45 degrees away from 90, left and right, basically, we also get the same point, well, which is not quite clear here, but this should be the same point. So this on this same line, we get 2 points, and these points are 90 degrees apart, basically. Sorry, yeah, 90 degrees apart, that means minus 45 and plus 45. And so see, we have them here. 90 minus 45 is 45. 90 plus 45 is 135. And they are at the same level, 7.07. And so that means that we can estimate the damping ratio as twice omega n divided by omega 45 minus omega, sorry, this is the other way around, omega 135 minus omega 45. This would be omega 45, this would be omega 135. So this thing is one other way to estimate the damping, looking at the forced response rather than the free response. Logarithmic decrement is only for free responses, because you let it vibrate and you see it die down, and you can see how many oscillations it takes for it to die down, or what is the ratio of two successive amplitudes. This way is a forced way. So you just extract the frequency response, and then by looking at this ratio tells you how sharp is this peak. So you can estimate the damping ratio in that way. Okay, that's it. That's done for question one. Well, once you know the damping factor, then you can find, oh, the support stiffness. What I didn't tell you here is that what happens if rho is 0? When rho is 0, see, all of these curves converge. And they converge because there's no dynamics anymore. That's statics. Okay? And so if this is x, this is the static x. So if you know the force and you know the deflection, you can find the stiffness. So this thing here is always k. It's quite interesting that you can see k in a frequency response function. So you can estimate k by just looking at the very first slice of your plot. And see, that's one way to be mean to your civil engineering friends, because your civil engineering friends that deal with statics only, they are restricted to this slice of the world. Okay, they see the world through that slice only. Whereas you are mechanical engineers, you see it in all full colors, okay, and all its complications, of course. Okay, don't be mean to your fellow civil engineers, though. Okay? But if you want, that there is a way, but don't. All right, let's go to question number 2. So we have the same system that is shown in figure 1, subject to this sinusoidal force of constant magnitude 800 newtons. See, the magnitude is constant, but the force is sinusoidal. The amplitude at very low frequencies tended to 8 millimeters. That means, see, I'm giving you the stiffness. Okay, so the amplitude, so this is the amplitude. Sorry, probably I should not call this K, because this is not K. X is in millimeters, okay? So this is not K in millimeters. So this is X0, which is equal to f0 over k. That's what I mean, but you can estimate k by looking at this. This is just x0. Okay, and the maximum amplitude was 10.91. Maximum amplitude means omega r. Okay, so it doesn't mean omega n. Just so you know that the maximum amplitude is not at the natural frequency, is at the resonance frequency. Determine the natural frequency, damping factor, and support. I mean, you can do this, guys. It's very easy. You just look at this, and you find the largest x happens when rho is equal to omega r over omega n, which is this number here, because omega r over omega n means that omega n goes away. So you can just find rho is this number here. So at that rho, if you put this inside here, you'll find that the largest x, and then you can also find at which rho it happens. And so you can just find at which rho it happens, and then you'll find the natural frequency. Once you have rho and you have omega r, you can find omega n. Damping factor, same thing. Once you have, what does it say? A very low frequency, 10 to 8 millimeters, and maximum amplitude. Okay, once you found, once you have this other information, you can find zeta. Again, zeta is unknown in this equation. Or you can even use this equation. Once you know that theta is 90 degrees, theta is 90 degrees at rho equals 1, you can estimate zeta. You have 90 degrees here. Arctangent of 2 zeta times 1 divided by 1 minus 1. Well, that's why you don't want exactly 1, because that's 90 degrees, of course. So you can't use this one, you must use this, because this doesn't give much information. Okay. And this support stiffness, as we said, we have 8 millimeters, which is x0, which is equal to f0 over k. So you can find k equals to f0 divided by x0. So f0 is 800, x0 is 8, so see 100 kilonewtons per meter. That is just a ratio. So it's quite easy. I gave you all the information here anyway. So once you know that this is 8 and this is 800, you can find x. Sorry, you can find k. And this one is, well, it's exactly the same. So a structure which may be modeled as the previous system is given as a small displacement from the static equilibrium position and then released. The transient frequency is 33 hertz. That is omega d is 33 hertz. And the amplitude is attenuated by a factor of 9.2 each complete cycle. That means the ratio of 2 successive oscillations is 9.2. You're given the mass of the structure, so you can determine everything else. Basically, that's quite simple. Let me check. Damping factor is easy once you have the logarithmic decrement. Undamped natural frequency is easy because you have the omega d and the damping factor, so you can find omega n. Support stiffness, once you have omega n and the mass, you can find k. Amplitude and phase of the amplitude relative to the excitation force when subject to a sinusoidal. Now that you have f0 and omega, you can enter here, you find f0 and omega. Omega n was given, zeta you found, so everything here is given. You can find x, and then you can find theta as well, because it's asking you for the amplitude and phase of these for a certain force and a certain frequency. And finally, I lost it. What is the resonant frequency and resonant amplitude if the amplitude of excitation remains constant? So that means what is basically omega r. Once you know omega n and zeta, you can find omega r. And what is the amplitude at omega r? You just put omega, you just find rho r, which is omega r over omega n. You place it here. Everything else is given. You find the amplitude. Easy. Yes.
Can you just change omega r for omega n?
What do you mean you can change omega r for omega n?
Do you find the
If it says find, yeah, you just place omega, but this rho is omega r over omega n. That's it. So rho is always omega over omega n. If you are forcing at resonance, that is omega r over omega n. If you are forcing at the natural frequency, that's omega n over omega n. That's one. Okay. Exactly. You just change omega, the first omega, the numerator omega to omega r. That's it. Because that's the only thing that changes with the external agent. All right. I believe that that's it. I'll give you 5 minutes break, and then we'll start on the vibration absorbers. Yes, Asham, this is exactly what we did last year. So there is nothing new so far. Now that we resume, we'll be starting with something new. Yes.
This session, can I just ask you a couple of questions about the course? I'll just clarify.
After.
Yeah, of course.
Yes. After the session. Yes. Yes, Eva, I see what you were referring to. You were referring to this part getting larger with damping, getting higher. That is transmissibility. You are right. That's a different thing. That is the ratio of two amplitudes. That it looks similar, but it's not exactly the same. Calculate torque is the equation. No, that's not torque. The torque, the friction torque is the friction force times the radius. And that's it. You don't need sine of theta. Where is this sine of theta comes from? Anyway. Yes, was great.
Questa formula da dove
It's a model.
sempre così.
Every time is different. It's a model. It's a way to draw a straight line on the water curve. There are so many ways, but I must be giving you the model. You can't come up with the model yourself.
Okay.
So this is based on this model.
And this relation here, which will
That's because you have
actual loading.
that's because you have repeated loading.
Okay.
Repeated loading is loading, unloading, loading, unloading. If you have fully reversed loading,
Yeah.
then you have sigma A is a number, sigma min is 0.
Okay.
So it's given in the slide.
So this is minimum.
No, that's mean stress.
I mean,
Mean.
okay.
If it's repeated
Yeah.
loading, then the mean stress is the same as the amplitude.
Then for this one,
Yep.
the formula is this one.
Yep. If it's Goodman, it's this, yes.
Why is the factor of safety?
What's the question asking? Allowable. So you can get up to the limit. That means safety factor 1. If we give you a safety factor, then you can use it. That means if you have a tiny bit more, it fails.
Okay. Then here is 0 to maximum sigma r. Is it not minimum to maximum?
What's minimum?
Because up and down. So is it not?
So what's sigma r? First of all, what are we talking about? Sigma r.
So there was a drawing in demonstration. I thought sigma r was from here to here. So no?
Oh, that's the range, the stress range.
Yeah.
Yeah. So the stress range starts from 0.
Yeah.
Because you have no alternating stress, up to the possible maximum range.
So it's from Okay, because I thought it was from here to here, so
Yeah, it
minimum.
is. So 0 means no sinusoid, no sine wave.
Okay.
Means sigma range of 0, that means constant stress.
But is it from here to here?
Yep,
Or from, but this is 0, isn't it?
that's it. In fact, the stress range is this. From here to here.
So it's not from 0 to maximum, it's from minimum to maximum.
Yeah, but what I was saying is that the sigma r
Yeah.
goes from a minimum of 0, so no alternating stress at all, to a maximum of 300.
So does it not go from 300 to minus 300?
Yes, it does go from 300 to minus. So sorry, can you show me again the?
Yes.
So it's the range that goes.
0 to maximum.
So the range is 398. So that means it goes from plus 200 to minus 200.
So from maximum peak to minimum peak. So it's max to mean.
Min to max, yes. Peak to peak.
Yeah. And then, so for sigma m is the mean, so it's this formula. What is sigma m?
The amplitude.
Amplitude.
It's the alternating stress. So it's the amplitude of the sinusoid.
Yeah, factor state is the same. And when is sigma e equal to sigma a?
Only when sigma mean is 0. Sigma m is 0.
Because in this case, sigma m is this,
Yeah.
but they still make sigma a equal to sigma e.
Because you need you want to, what do you want to follow? Can be, because if sigma a is the same as sigma, this is already 1.
Yeah.
So you can't have any more mean stress. This must be 0. If sigma a is the same as sigma e, that's it. That's 1 already. This one must be 0. Sigma m must be 0.
Okay, so it's not
See what I mean?
possible.
So that's.
But the formula is sigma a. Where is it?
So sigma a is sigma e only when sigma m is 0. Because that's the formula.
No, look at it. Thank you.
First, okay. So we don't use polar moment. No, you don't use the polar moment. That doesn't mean anything. But that would be the torque, the internal torque of the shaft. That's not what you're calculating. You're calculating the friction torque between the shaft and the wheel. That is an external torque on the shaft. It's not the internal. That T is the twisting torque on the shaft, which is a completely different thing.
Like kind of like you just like as you get further away from certain pressure, every kind of pressure. My body's done. Oh yeah, she got some of it. She's still on the effort. So the brief you got was different. Yeah. I mean, I had to send them my artist. Right, it brings them yeah, anything. Not today. It's like, okay, so with the bridge, you go like this, but now when we're trusting, You don't break a table. You cannot break a table. You can break a table, do a pair of shots, but you can't break a table. One leg longer than the other. You break like an ankle. One leg is longer than the other. How lucky. I've seen you online. That could be more of your shoulders. Go down.
Is this your report?
No. Go down. No, a bit more.
Yeah, that's what you mean by jumping, isn't it?
Yeah.
Yeah.
So every sheet on that pressure, how it's font size.
So basically, it says, so we need to say like what determines how it's split.
How are you posting your graphs?
I'm doing that.
He does explain this. Anand does explain this. Excel.
Sure, why not?
Come on.
It's just
Maybe we fly on that.
it's just numbers.
Depending on what.
You know the like every 5 all sigmas equals 5.
It would be.
And then you use the curve.
Yeah. But that I guess is still counts because how it shows how the food stress changes. Just like contact pressure.
All right, let's resume. Come on.
Oh, you can't change
Guys, come on. So now let's start with the vibration absorber. I'm just copying basically the 3 equations that you need, and they will all be what you need. They'll just these are the only things that you need at all. So copying this one, K2 over K1 plus K2 minus omega n squared m equals again K2 plus K3 minus omega n squared m divided by K2. And the last equation probably is the characteristic equation, that is this beast here. That would be omega n to the power of 4 plus minus K1 plus K2 over m1 plus K2 plus K3 over m2 omega n squared plus ultra beast K1 K3 and K2 K3 divided by m1 m2 equals 0. Okay, that's all you need. So these are the formulae, and these formulae are telling you what's happening for a system with a certain mass 1 and K1 and a certain mass 2 and K2. Okay, and in this case you also have K3, which is a spring that sits here if you need. Okay, so what happens when you have when you have 2 masses attached to each other? You have 2 resonance frequencies. And all of these plots are done at zeta of 0, because as you can see, we have no dash plots anywhere. But if you just add dumping, nothing really changes. It becomes a bit more complicated. But you can still have a dumped effect on the single mass. So the single mass would look like this. The single mass will look like this. But as you can see, we can reduce this amplitude, say, down all the way down to here. So by a lot, because remember, this is a logarithmic plot. This is a log scale plot. By just adding another mass. Problem is that mass must be tuned to a specific frequency. And what is the tuning frequency? That means that the extent, whatever is driving mass 1 at a frequency of omega, in order to get this equal to 0, x1, which is the displacement we are interested in order to make this 0, we must make the numerator 0. How do you make the numerator 0? The external agent omega must be exactly tuned, well, omega to n, basically, which is our added mass and spring, must be tuned to the frequency of the external agent omega. If this is happening, then you take the entire mass 1 and then you stop it completely, irregardless of what's going on or what kind of force it is applied to. Even if you have 1,000 newtons, 10,000 newtons, 100,000 newtons, if it's driven at this frequency here, where omega is equal to omega 2n, this is the completely absorption condition. So this is the absorbing condition, is this one. If it's tuned, the mass doesn't move at all. Now, you can't always make it perfectly tuned, so it will move a little, but it still moves. A little means in this region, so it still moves much lower than it was moving without the absorber. Problem is, you never get something for nothing. So in order to get this advantage, you are getting a disadvantage. The disadvantage you are getting is that you are creating 2 instead of 1 resonance frequencies. So now we have 2 potentially breaking conditions. But as long as it operates in between these 2, everything is fine. Everything checks out. Again, should not be exactly here and here, because as you can see, if I'm here, this is detrimental. So I'm still getting a more amplitude from the absorber than I was getting from the single mass. Okay, but at least it's not breaking. It breaks when I am here or here. All right, so let's solve tutorial 1. And I'll do 1a and 2a, which are basically use the frequency equation method to find the natural frequencies and mode shapes of this system here, which is a shaft, torsionally vibrating shaft, and a system of 2 masses and 2 springs. So if I do, let me do question 1a. And this is a shaft. The certain torsional spring. Torsional spring is KT. And we have a certain I1 and I2. And these are the mass moments of inertia of the 2 rotors. What is this? Oh, is this? I don't need this. Oh, there you go. So one is 10 and one is 15. I1 is 10. I2 is 15. And the mass that connects them is K. K is 10.2 kilonewton meters per radian. 10.2 kilonewton meters per radian. And of course, I1 is kilogram meter squared and I2 is kilogram meter squared because it's a rotational system. Let's find the natural frequencies of this thing. Now, these are two masses attached by a spring, effectively. So you can just go here and use this one. And this one gives you K1 is 0. K1 is 0. K3 is 0. Do you agree? So this goes away, this goes away, this goes away. So we are just left with 2K2. So we have lambda squared. So we turn this on omega 4 to lambda squared, because otherwise we don't know how to solve a fourth order equation, but we know how to solve a second order equation. And so my equation becomes lambda squared minus K2, 2K2 over M. No, it's not this 2, it's not this easy, because this is minus K2 over M1 plus K2 over M2. Lambda equals 0. That's because this term here is all zeros, 0 over M1. And remember, if you solve this, you get that lambda 1 is something and lambda 2 is something else. Lambda 1 is 0. Can you see why lambda 1 is 0? Because if I put 0, the equation is satisfied. So I can take lambda as a subject, and this becomes okay, it becomes this. So I can get rid of lambda here. And so the other lambda is K2 over M1 plus K2 over M2. And this corresponds to a lambda of, let me do the calculation with Wolfram alpha. This is 10.2. So I get 10.2 divided by 10 plus 10.2 divided by 15. That's 1.7. But 1.7 is not what I want, because 1.7 lambda is omega squared. I want omega, so I have to take the square root of that. And the square root of that is 41. Well, this is 41.23. What's going on? 41.23. Did I miss anything? Yeah. What did I miss anything? Yeah, I1 and I2. So what do you mean? You should be using just this frequency. Did I copy this wrong? I don't think I did. K2 over M1 plus K2. Yes. In kilonewtons. Yes. Thank you. Thank you. See? Thank you. Units. It's in kilonewton meters. So it's 10,200 Newton meters per radian. Thank you very much. See, this is very easy to get it wrong. If you don't care about the units, as I am doing right now. There you go. And so let me just rearrange this. This is 10,200 and 10,200. And this becomes 1,700, for which the square root of this is 41.23. Very good. 1,700, thank you. This is 17,000. 1,700 or 17,000? 1,700. Okay. And so the square root of this, oh, there you go. So that means that omega 1 is 0 and omega 2 is 41 point what? 41 point whatever. 41.23 radians per second. And check. Why do we have an omega 1 of 0? What does it mean? Yes.
Did you get the values for the mass?
The mass is I0 and I1 and I2. We are using now. So instead of using M1 and M2, these are the rotational equivalents. So this is KT, and M1 is I1 and M2 is I2. When we deal with rotation, we have to substitute whatever is K with KT. So whatever stiffness with rotational stiffness, and whatever mass with mass moment of inertia, always. Okay. So don't get thrown off if at the exam you see a rotational system. It's just a matter of using different units, basically. That's it. All right, see what happens that omega 1 is 0. Why is omega 1 0? What does it mean, omega 1 0? This means that it doesn't vibrate. In fact, it doesn't vibrate. See, that's a shaft. That rotationally, the two masses can just rotate as a rigid body. And if they rotate as a rigid body, there is no vibration. It's just a continuous rotation. Yeah? So omega 1, which is the first natural frequency in reality, that thing is a rigid body mode. And you'll find that the rigid body mode is when A1 is the same as A2. So A1 and A2 go in the same direction at the same rate. Instead, if we use this one, so you can find A1 and A2 either in this way or in this way. So let's copy this one. And so I have this one is A1 over A2 1 if I use omega 1. And then I have A1 over A2 2 if I use omega 2. As you can see, if I use omega 1, what happens? K2, remember, K2 is KT, K1 is 0. If I use omega 1 of 0, I get K2 over K2. So this one becomes 1, which means that A1 is A2, which means rigid body motion. So no oscillation. If instead I take A1 over A2, 2, which is the second mode shape, and the second mode shape uses omega 2. So this gives me minus 1.5. Okay, I'm not doing the calculation. So that means that A1 is minus 1.5 A2. And so if I plot it on a mode shape diagram, I get that this mass moves, say, 2. And this mass moves 3, 1.5. This moves, say, 2 units. And sorry, it's the other way around. If this mass moves 2 units, A1 mass 1 moves minus 1.5 A2. It moves 3 units in the opposite direction. You agree? So this is 2, this is 3, which is 2 times 1.5 minus 3. Okay. And so this is the mode shape. And that means in between these two, there is a node here, node, for which the amplitude is 0. So if I twist this in this way, there is one point on the shaft that doesn't twist. That's what I'm saying. And again, the fact that I've chosen these two is completely arbitrary. Because if this is 1, this is minus 1.5. If this is 4, this is minus 6. So it doesn't matter. Because these things are the same up to a scale factor, which might ring a bell. What is the same up to a scale factor? Eigenvectors. Remember, those were the same because they were just pointing in a certain direction. That doesn't matter how long they are. And I will show you next week that mode shapes are exactly the eigenvectors of a certain eigenvalues problem. Okay, I think that's it for this one. Let's do, well, the other one, guys, it's just exactly the same thing. So this one, you solve it in exactly the same way. K1 is 6K, K2 is 2K, K3 is 0. And so in this case, you just have A1 over A2, which is 1/2 for the first one. For this omega 1n, you get 1/2. That means that A1 moves half as much as mass 2. And it makes sense because mass 1 is 4 times as massive. See? So of course it will move less. And A1 over A2, you get minus 1/2. So in the first mode shape, these two will move in the same direction, but not at the same rate. Mass 1 will move 1 unit. Mass 2 will move 1 unit. Mass 1 will move half a unit. Mass 2 moves 4 units. Mass 1 moves 2 units. And they oscillate back and forth, where the amplitude of oscillation of 2 is larger than the amplitude of oscillation of 1. But they move in phase. Whereas the other one, A1 over A2, at this other frequency that you can find with the frequency equation we just said, is minus 1/2. So that means that, yeah, it will still be moving half as much, but in the opposite direction. So they will always be moving like this. Let me see if I can show you something like this. It's very hard to make it work because I have to move my hands at different rates. So it would be something like this, where this my right hand is moving more than left hand. Okay. All right, so let's solve question, I'm not sure which one, question 2, question 3, question 4, 3, 4, 5. So let's go to question 3. Question 3 is now vibration absorber. We have a jig that is used to size code and contains a screen that reciprocates with a frequency of 10 Hertz. That means that this screen is being driven at 10 Hertz. So these 10 Hertz are the omega of the external agent, so not the omega of the system. The jig has a mass of 230 kilograms and has a fundamental frequency, this is the natural frequency of the system, of 6.66 Hertz. Now we want to install a 55 kilogram absorber to eliminate the vibration of the jig frame because it has a screen and this screen is vibrating. Now, what is the required absorber spring stiffness? Ideally, what we found is that, we found a bunch of scrap metal, 55 kilograms heavy, in the warehouse. Can we use it with an appropriate spring to create an absorber for this machine? Yes, just select an appropriate spring. And also, when we install it, then we are removing this fundamental frequency of the single mass, but we are creating 2 more frequencies. That's what I told you. So what are these two frequencies that we are creating right now? Okay, that's extremely easy. Once you have your formula sheet, this is question 3. So let me copy the data first. So we have omega of the driving force, it's 10 Hertz. Omega n, so the mass 1, that's the mass of the main mass, is 230 kilograms. Then we have omega n, which is omega 1n. Remember, omega 1n, if I go here, omega 1n is the omega of the system, is the omega of mass 1 as if it was the only mass present in the system. So omega 1n, this is what I'm giving you here. Omega 2n is the omega of the absorber as if it was the only mass in the system. So this is omega 1n, and that's equal to 6.66 Hertz. So 6 and 2/3. M2, so the mass of the absorber, M2, is 55 kilograms. What is K2? I'm asking here, what is K2? First of all, let's use the absorber equation. So I'm going to copy and paste them as they are. Both of them. There you go. You know what? I'll copy and paste everything because this is my formula sheet for the absorber. I'll place it right here. Okay. There you go. That's all I need. I don't need anything else to solve for the vibration absorbers. It looks complicated, but in reality, it's very easy. So it's all a matter of reading and using your knowledge to understand what these quantities are. So what are the numbers I've been giving you? All right, so we want to find K2. What is K2? We know that this is the amplitude of vibration of the jig screen when we connect the absorber. And we know that we want this to become 0 because we can select an appropriate K2 so that this thing becomes 0. What is the condition for which this becomes 0? How do I make this thing 0? How do I make this thing 0? It's a fraction. When is a fraction equal to 0? There's only one condition. The numerator must be 0. The denominator cannot be 0 because if it becomes 0, it shoots up to infinity. So the only way for x1 over x0, this thing to be 0, is for the numerator to be equal to 0. And when is that numerator equal to 0? When omega is equal to omega 2n. Now, omega is given, so we can't change omega because this is being driven at 10 Hertz. So we must fit in an absorber that has an omega 2n of omega. So the absorption condition is omega equals omega 2n. But omega 2n is also equal to square root of K2 over M2. And lo and behold, we just found K2. See how easy is this? The equation looks horrible, but it's actually quite easy once you have understood what the question is looking for. And so I can just rearrange K2 is just omega n squared. So omega 2n squared, which is just omega squared, basically, times m2. And that's, so I can just look at this as saying that K2 is 2 pi times 10 squared times 55. Which is equal to this many newtons per meter. Okay, remember omega is not F. F is in hertz. So this thing that we are given, I should not be calling them omegas, really, should be calling them F. Because they are in hertz. Just for consistency of, I mean, it's not a mistake if you call them omega, because all the engineers call them omega all the time anyway, because it's just the same thing in a different unit. But let's be consistent, and you know that omega is always 2 pi F. Okay, so you know how to pass from one to the other. All right, that's it. What does it say? Determine the required absorber spring stiffness. That's what we did. Determine what will be the resulting two natural frequencies of the system. Okay, now the question is, let's look at this equation again. Now we know that at omega, with this omega fitted in, this would be 0. Easy. But when will this explode instead? So the denominator must be 0 now. So this thing will explode when the denominator is 0. So we have to solve for the omegas, the unknown driving frequencies that make this thing equal to 0. So now omega is not this anymore, because we use this to design the absorber. And now we are asking ourselves, what if the driving force is changing frequency? Will this explode? At which frequencies must be mindful of? So I must monitor this thing now. When you fit a vibration absorber, you must continuously monitor it so that you are sure that the driving force is always 10 hertz or close to 10 hertz. Resonance condition or resonating condition means that this thing, that I will copy and paste, this thing equals 0. And so this is just, I mean, it looks complicated, but K1 is given, K2 is given, omega 1n you can find, omega 2n you can find, omega you can find. So, sorry, K2, omega is the only unknown. The only unknown here, unknown is omega. So you have omega equals, since it's omega squared, as you can see, these are all squared, these omegas are all squared. This is a second order equation. So omega has two solutions. And those two solutions are omega low and omega high, which are the range. They define the extremes of the interval at which this thing is safe. Again, not exactly the interval at which it's safe, because, well, safe, it's safe. But if it's more towards the edges, the absorber becomes detrimental there. So let's solve this with Wolfram alpha, because why not? And let me copy it. Let me copy this thing. Oh, let me copy this thing. Oh, come on. There you go. So this is open bracket 1 plus K2 over K1 minus X. X is my unknown, so I'll call it X, divided by omega 1n, omega 1 all squared, times 1 minus x over omega 2 all squared minus k2 over k1 equals 0. Now, I want to put numbers here. So k2 was 2.18 10 to the power of 5. 2.18 E5. Omega 1 is 6.66. Oh, see, we can do this in hertz. We can do this in hertz because these are all ratios. If I put hertz, omega 1, if I put F1n and F2n instead of omega 1n, right, I get in X, I get it in hertz rather than. Is it clear? Can you see that? I'm not doing any kind of wild magic. Instead of omega 1, I put 6.66 in hertz. And this I put 10 because I know that omega 2n was equal to the old omega. And K1 is, how much is K1? Oh, I need to find K1. Yeah, and I need to find K1. K1 is 2. Let me copy this. So K1 is 2 pi times omega 1, which was 6.66. So this is omega 1. Omega 1 squared times the mass of the jig, which is 230. So 402, 750. I put 402, 750 here. And here. And I solve. Ta-da! See? So these are the 4 solutions to this equation. But we don't care about the negative side. We care only about the positive side. And so the two solutions are 5.71 hertz and 11.64 hertz. So omega low, well, let's call this F low and F high. F low is 5.7. And F high is 11.64. See, this mass and this stiffness have helped, but not a lot. So my driving frequency is 10 hertz. Now I have this force can go a lot lower in frequency, and that's fine, but it can't go much higher. So we must keep this very monitored. If you want to increase that range, then you need a different combination of K2 and M2 in order to give you the same omega, but in order to have a larger range, you have to have a larger mass. So if you increase mass 2, so in turn increase K2, you have a much stiffer spring with a much larger mass, so they are still tuned at the same frequency, but now the range becomes larger. So increasing mass enlarges this range. But there's only so much mass you can add, which is freely vibrating. You agree? So otherwise, it becomes a bit unwieldy. Okay, so that was question 3. Now let's do question 4. This is probably the hardest question of the tutorial. Question 4. So question 4, we have a pipe. In a second, let me check the chat. So if you turn on off the shaker, the frequency will decrease from 0 to Z. Yes. So Asham is asking, if you turn off that external agent, that force will probably go from 10 hertz to 0 hertz, passing through all the frequencies. So that means that when it hits 5.71, when it hits 5.7, where is it? there you go, when it hits 5.71, this will mean it will break the system. You are correct, well, almost correct. So what is happening is that when you turn it off, the force, the magnitude of the force will also be decreasing anyway. So yes, it will be experiencing vibration, but while the force is decreasing. So the effect will not be as much, especially if it's turning off very fast. If you just turn it off and it stops, that's fine, because it passes through 5 very quickly. Have you ever noticed when you are in your car and then the crankshaft of your engine is basically responsible for most of the vibrations that happen in your car when you're not driving, when you're not actually driving? If you're standing still, all the vibration comes from the crankshaft. And so if you are at very low RPMs, what happens? And then it stops. Okay, it vibrates a lot and then it stops. See, if you remove your pedal, if you remove the foot from the pedal, what happens that the RPMs will go down and down and down and down and down. Then at some point you will shake like crazy and then everything stops. The shaking like crazy is because that's exactly what, there is no vibration absorber, but the natural frequencies of the crankshaft, the first one is always lower than the RPMs you get, the general usual, because it's designed on purpose like that, because you are never supposed to be at that low numbers of RPMs. When you are at that low numbers of RPMs, it's shaking like crazy because you're hitting the natural frequency of the crankshaft, the first natural frequency of the crankshaft. Okay. Eva is asking, I'm really sorry, I have to go. Will the recording? Yeah, of course. The recording will be available as soon as it's ready, a couple of hours after I stop the lecture. Then Zoom sends me an email, says, your recording is ready. I'll download it. Bye, Eva. I don't know if she's still here anyway. No, she is. Bye. What I was saying, question 4. In a certain refrigeration plant, a section of pipe carrying the refrigerant vibrated violently. That means we are hitting the resonant frequency. Vibrated violently at a compressor speed of 232 revolutions per minute, RPMs. These are RPMs. So at 230, if you drive your compressor at 232 RPMs, the pipe it is attached to starts shaking violently. You don't want that. So to eliminate the difficulty, it was proposed to clamp a spring mass system like a stock bridge damper. Remember the stock bridge damper that I showed you in the lecture? Those two big masses attached with a small cable that you just attach to the power lines or the lampposts. You can attach them to pipes as well. You want to clamp a spring mass system to the pipe to act as an absorber. So for a trial test, so we don't know anything about the pipe. We just know that it vibrates violently at 232 RPMs, which corresponds to these many radians per second. So in a first instance, we just attach a mass of it, attach any mass with any spring to it. Say we have a 1 kilogram absorber tuned at 232 RPMs. And we can measure then that we have two natural frequencies now of 198 and 272 RPMs. Now that we have this information, we can find the properties of the system, K1 and M1, which we know the ratio, but we don't know K1 and M1. There are infinitely many combinations of K1 and M1 that can give you the same ratio. And then now that we have this information, we want to design a proper absorber, not a trial absorber, a proper absorber that has the natural frequencies outside of this region, 160, 320. It must be outside of that, because we know that the compressor will be operating along in those speeds. So your natural frequencies, omega low and omega high, should be away from that range, operating range of the compressor. So what must be the mass and the stiffness of the stock bridge damper, which is a mass damper? So let me draw. This is the pipe. So we have a compressor. Let me see if I can draw it nicely. There you go. That's a compressor. And there's the pipe attached. And this thing is vibrating a lot. And so let's attach a stock bridge damper. With a certain mass and a certain stiffness. And let me copy all the information. So we know that this goes awry at omega 1n 232. Sorry, not omega 1n. This is omega only because it's the driving agent. 232 RPMs. Then we have a trial test. So trial. For the trial test, we have 1 kilogram mass of the absorber tuned at 232 RPMs and resulting in omega low of 198 and omega high of 272. These are the trial information. And then for the actual one, we want omega low and omega high to be omega low should be smaller than 160 and omega high should be greater than 320. And we need to find K2 and M2. Okay, so that's what I'm looking for. So I have to apply the equation twice, basically. First for the trial absorber, and then to find the actual absorber. Now, let's find K2. So let's start from the trial. So from the trial, K2 is omega 2n squared M2. So this gives me already a, so this is 232 RPMs. So let me duplicate this because I'm going to need this equation later to solve it. So we have 232 RPMs. How do you pass from RPM to radians per second? 2 pi divided by 60. So times 2 pi, 2 times pi divided by 60. And this is square, everything is squared times the mass 2, which is 1 kilogram, of course, that's 590.24 newtons per meter. Okay, so this is K1, K2. And now let's use the absorber vibration, the absorber thing. I'll copy this. I only need mass 1. I don't need anything else. So I'll put this here so I can use it. And I will use it. I know omega low and omega high. So I know the omegas that make this thing equal to 0. And I can find K1. Do you agree? and I can find omega 1n. How many unknowns I have here? How many unknowns I have here? And well, let me draw. So let me spell it out. I know the omega low and omega high that make the denominator equal to 0. So I can just copy this thing and put it equal to 0. And so I can turn this into two equations. One, if I substitute omega low instead of omega, and the other if I substitute omega high instead of omega. So using omega low, this is equation 1, this is equation 2. So using omega low, I get this thing. Using omega high, I get this thing. You agree? These are two different equations because we have different values. What are the unknowns? What are the things that we don't know? K2 we just found. K2 is given. K1 is the stiffness of the pipe that we don't know. We have no idea. K1, this is one of my unknowns. Unknown 1. Omega 2n, do we know it? Yes, we do. It's given here. Okay? Omega 2n. So the only thing that is left is omega 1n, which is the natural frequency of the pipe in isolation. So this is the other thing that I don't know. And as you can see, two equations, two unknowns. Quite a pain to solve, but still two equations into unknowns. It's painful, two equations into unknowns. So let's solve it with Wolfram alpha. And I'll use this one twice. So K1, we don't know. So let's call this X. K2, we found earlier, 590.24. Omega 1. Sorry, omega low and omega high. If I use RPMs, I will get a result in RPM. Okay, so I will get omega 1n, which is my unknown, and this is my y. This is omega low, 198 RPMs. This is 198 RPMs, and this is omega 2n, 232 RPMs. Okay, so this is my first equation with x and y unknown. X is my first unknown K1, y is my second unknown omega 1n. And I copy this and comma, I put it here and I put it in curly braces. And my other equation is the same, but instead of 198, I have omega high, which is 272. I have it here and here. If I solve it, ta-da, come on. Can I solve it? Do I do solve? Didn't get, oh, there you go, these ones. So where are the solutions? There you go. So my first unknown is 5,808 newtons per meter, K1. My second unknown is 232.12 RPMs, because I've used X, K, and Y omega. So if I solve this, solving, you get K1 5808.4 newtons per meter, and omega 1n 232.13. 3.14 RPM. See, it was violently shaking because at 232 RPMs, it's very close to the natural frequency of the pipe. That's why with the compressor at that speed, it was shaking. And now, I would argue that an engineer that has designed this would have known the operating range of the compressor and would have made sure that there were something in place. So every time you put a vibration absorber, it's generally to correct an issue. Millennium Bridge, same thing. Renault Formula One car, same thing. Because you can't, well, in that case, it's a bit different because you can't predict all the possible things that are going on, but you can always tune it to the natural frequency of the oscillation so that when it gets driven at that oscillation, you know it's zero. All right, now that we have the properties, so now we have full information on the pipe. Now that we have full information on the pipe, the unknowns change. So now we want to find what are K2 and M2. So the new K2 and the new M2. So the K2 new and M2 new. So that such as the omega low and omega high are two other numbers. And so again, this is just exactly the same thing. I'll call this equation 3 and this equation 4. I have omega low star and omega low star and omega high star and omega high star. So these are the other two omega low and omega high. And my unknowns are not K1 and omega 1 n anymore. My unknowns are now K2 and M2, which is inside omega 2n. Okay, or is it, does it say? Yeah, K2 and M2. So K2 is hidden inside here, is here, here, and here, but M2 is only here. So I'll say, let's find K2 and omega n2, and then we find M2 later. That's, we know the relationship between the two. All right, so turn this on. That's it. I just go to Wolfram alpha again, and I just change my variables around. Oh, it's 4. Oops. Sorry, guys. Is there anyone outside waiting for me? Hopefully not. So we can splurge a little bit. Where am I? Here. So let me just change this thing. So my unknown is now K2, because K1 is 5808. So K2 is X. This is 5808.4. This one, A low nu, sorry, omega low nu is 160. Well, no, guys, no, you do it yourself. Okay, it's easy. You just have to change variables. So don't worry about it. You solve this and you find the new. K2 new equals, and you find omega 2n new equals, and then you find from here, remember that M2 new is just omega 2n new squared divided by K2. Okay, easy. Any questions? Is it probably no? It's the other way around. It's the other way around. This goes up, and this goes down. Yeah. Any questions? No? Okay. Thank you very much, guys. Let me stop recording. We have gone a little bit over. That's fine. Thank you so much for being online. Bye.